Well, what's happening, everybody? All right, we're continuing our applications of trigonometry section. In the last video, we learned how to use angles of elevation and depression to solve problems. In this one, you're going to learn to use compass points and bearings to solve trig problems that involve directions. All right, now I need to explain what compass points and bearings are, and then we're going to work on one example, and it's a pretty tough one, honestly, of a problem in which there is direction involved, other than just left, right, up, down, that kind of thing. Okay, so when I'm talking about compass points and bearings, I'm talking about ways for you to describe which way you're heading on a map, basically. So you're going to see things like east and west and south and north and that kind of thing. And you're going to see directions written in this compass point form where you have an east and a south within the same thing and then an angle between them. First one is east 30 degrees south. And that implies a very specific direction that someone will be traveling. Of course, you know north will be the top, east would be to the right, and then south and west on the compass, correct? Well, if you're told to go the direction east 30 degrees south, what it means is that you face east first, and then you turn 30 degrees to the south. All right, so there's my line going east, and then if I turn 30 degrees to the south, that would be this way. This would be going in the direction east 30 degrees south. Okay, now let's try that with north 70 degrees west. If I want you to go that direction, then you're first going to have to face north, and then you're going to have to turn 70 degrees to the west side. So turning west from there, is it this way? That's about 70 degrees probably. And you see the 70-degree angles between north and west. All right, there's north 70 degrees west. Now, by the way, every one of these directions, with the exception of the next one, I suppose, but most all of these directions can be written two different ways. The east 30 degrees south could also be south 60 degrees east. Because if you faced south first and then turned 60 degrees in the easterly direction, you're going exactly the same direction as the east 30 degrees south. Similarly, we could have changed the north and the west here in the north 70 degrees west, and then use this angle, the angle between west and north, and said that this was west 20 degrees north. All right, now sometimes you'll just simply see two directions like northeast, northwest, southeast, or southwest, and no angle between them. And whenever you're given just southwest or just southeast, what is implied is that you're going exactly in the middle of those two directions. Or in other words, there's a 45-degree angle involved. So southwest would be going this way, and you'd have 45 degrees on either side of that. Okay, so those are compass points, and when you see a problem that says that somebody walked north 20 degrees east and then turned south 70 degrees east, this is what they're referring to. Now, there's another way to be able to describe direction other than the compass points, which work very well, and that's using bearings. More specifically, three-figure bearings. And what a three-figure bearing is a way, it's kind of like what planes use, by the way, whenever they're flying. It's a way of telling the direction that you're going in relation to north all the time, okay? So, whenever we're working with three-figure bearings, what we're going to do is we're going to assume that the direction north is 0 degrees. And then we're going to rotate clockwise. And as you rotate clockwise, well, that would make 90 degrees your east. And then 180 degrees would be south. And then if you were traveling 270 degrees, you would be going directly west. And then if you go all the way around, of course, 360 degrees corresponds with 0 again. So if I'm traveling on a bearing of 140 degrees, well, that's going to be between 90 and 180 degrees, first of all, so we know that's going to be southeast. And, well, you can imagine where 140 degrees would be there. It would be 40 degrees shy of 180. So this would be the direction that we're going. And 140 degrees would be the angle that forms with the line going north. Okay? Now that could also be referred to, if you wanted, for instance, as south 40 degrees east if we went back to the compass points. Those mean exactly the same thing. Okay, well, then 80 degrees. That's less than 90 degrees, isn't it? If 90 degrees is right here, then 80 degrees is 10 degrees shy of that. This would be a traveling or a bearing of 80 degrees. All right, and then 240 degrees. Well, we've got 90 to the east, 180 to the south, 270 to the west. 240 is between 180 and 270. It's going to be a little closer to the 270. So this could be our 240 degree bearing. It would be 30 degrees shy of reaching 270, and we're measuring all the way from north around. That's where the 240 degree angle is located. All right, now we're going to do one application problem in this video because they just do tend to take a long time, these particular applications. And it's going to happen to be using the bearings that you see right here. All right, problem says that a helicopter flies 140 kilometers on a bearing of 100 degrees from city A to city B. It then flies 200 kilometers from city B to city C on a bearing of 65 degrees. How far and on what bearing must a helicopter fly to return to city A? Well, remember that in the previous video I said if you're not given a picture for a problem involving trigonometry, you ought to draw one, and that's the case here. And this picture is going to be a little bit different than the ones that we kind of drew in the previous video. The ones with angles of elevation and depression, I call those the Super Mario Brothers view, the original Super Mario Brothers, where you're looking from the side and the top of the screen is up and so forth. Now we're switching to what I would call a map view, so maybe a Super Mario World view, if you will. So we're going to be looking at this drawing as if we were in a helicopter or in a hot air balloon looking down on it, or if we're just looking down at a map, of course. And I think you can see why we choose that, because we're talking about directions between cities here. What I want to do is I want to go ahead and begin by labeling city A. So let's put a point here, and let's call that city A. And then I want to show that we're traveling from city A to city B on a bearing of 100 degrees. All right. Now, in order to get that direction correct, what I want to do is I want to kind of draw a mini compass here through point A, because that'll help me see where 90 degrees, 180 degrees, and all that kind of stuff is. And it'll help me get this line going in the correct direction. 100 degrees is just past 90 degrees, isn't it? Because remember, we're starting in north here, so there's 90 degrees. So about this way is going to be the path from city A to city B. All right, there's city B. And it is 140 kilometers away. Right. Now, we said this angle was 100 degrees from here. I would like it in relation to this line right there. That's a 10 degree angle. It was 10 degrees past 100. All right, well, after the plane flies that 140 kilometers from city A to city B on that bearing that I gave to you, it then flies from city B to city C on a bearing of 65 degrees. And it was a 200 kilometer distance. Okay, so to show that the plane is flying at a 65 degree bearing, I'm again going to kind of put a little mini compass through city B, so I have an idea of where 0, 90, 180, and 270 are. And then I'll draw a segment that goes in the direction of 65 degrees, which is going to be closer to 90 than it is to 0. All right, now one more thing to consider in your drawing here, if you want it to look as real as possible, is that the helicopter is flying further this time, 200 kilometers, than it did for the last leg. So I'm going to try to go in the 65 degree direction, and I'm also going to make this a little bit longer than the previous segment that I made. So let's say that this is where city C is. All right, 200 kilometers. And the 65-degree angle was right there. All right, and then we want to know how far and on what bearing must the helicopter fly to return to city A. So we know there's going to be a return trip from here down to there, right? All right. Now here's where this kind of gets tricky. Hopefully you understood the picture okay. We've talked about the bearing stuff that you need to know. But this triangle that we created right here is not a right triangle, and all the trigonometry we know currently involves right triangles. In some way, we need to be able to create right triangles that can help us find the distance that we're trying to find and the bearing that this helicopter would travel from city C back to city A. And here's the way I want you to make those right triangles. What I would like you to do is basically circumscribe, for lack of a better word, a rectangle around this triangle, like this. And what we've done by drawing that rectangle is we've created several different right triangles. All right, I'm going to highlight a couple of them and then I'll erase that. For instance, there's a right triangle. Here's a right triangle. And here's a right triangle. And we can use the trigonometry that we know in order to be able to find out measurements within those specific right triangles. Yeah, maybe I don't need to erase that. I'll leave the highlighting on there for you. But I am going to move this picture to a screen where I got a little bit more room to manipulate it. Now, before the actual solving takes place, there's a couple things that we ought to point out. And that, first of all, is where is the distance that we're trying to find? We're trying to find this distance right there from city C to city A. So I'll label that as X. Secondly, where is the bearing that we're trying to find? Well, this is the path of the helicopter, and we essentially want to know if we were to have a line going north, what is the angle that this line would form with that one? And so we'd have to measure all the way around right here. Let's just say that's alpha. That's an angle that we would need to be able to determine in order to know the bearing that this helicopter was flying at. Okay, well, both of those things can be found if we use this first right triangle that I drew. That now the highlighting isn't so great just because it's a small triangle, but I'm going to use the arrow right now. This triangle right here. Okay, and we've got the right angle for that triangle here. And the distance we're trying to find is the hypotenuse. And if we can find this angle, can you see that angle right there? I'm going to call it theta. Then we can use that to help us find out what the actual bearing is. Okay? Because that's the angle between 270 degrees and the path that we're taking. We know the bearing is going to be like 260, 265, something like that, right? That's what it looks like at any rate. Okay, but right now we can't do anything with that right triangle because we don't know any of its sides. All we know is that there's a 90-degree angle in it, and that's it. So we're going to have to use these other right triangles to help us out. Now let me start labeling some things that we're going to try to find. I would like to find this distance all the way from here to here, because that's one of the sides of the right triangle that we're going to ultimately work with. So let's say we label that as Y. And then I'd also like to find this distance right here, that little one, and I'm going to label that with a Z. How am I going to find that? Well, that distance Y happens to be the same as these two distances right here from the other two right triangles. I'm going to label this one as an A and this one as a B. It's just going to help me keep my work a little more accurate if I'm labeling what I'm finding. And that Y is going to be equal to A plus B. All right, and so you see I know one of the side links in each of those right triangles and an acute angle measure. I'll be able to find those distances A and B. And then as far as how I'm going to find the distance Z, well, I'm going to find two other distances. Let's say this one right here, the left side of that yellow right triangle that I made. And I'm going to find the right side of the orange right triangle that I made right there. And then ultimately we'll say that Z is equal to D minus C. And I think you can see why that would be. All right, so now to find all those little distances A and B and C and D that we're talking about. We've got one more thing to do before that's possible. We do need to know what are the acute angle measures within each of those right triangles. So let's use the right angles that are formed. You see how there would be a right angle here between this horizontal line and this vertical line? And we got a 10-degree angle right there. Well, that means this is going to have to be 80 degrees here. And so to find the value of A, well, we can use a simple sine ratio. The sine of that 80-degree angle would equal A over 140. Now, I'm not going to do a lot of explaining where the work comes from on this one because there's going to be so many trig equations that we're going to use, but I trust that you can solve that equation for A. And to three significant figures, you're going to get 138. All right, so this distance is 138 right there. Then, let's find the value B. You see the 65-degree angle between the vertical line and this line BC. Well, that's going to make this angle 25 degrees. Those are complements of one another. So then I can make the equation that the cosine of 25 degrees is equal to B over 200. And get that B is approximately 181. Now, one other thing I forgot to mention is that I would like you to kind of store these the actual numbers that you get on your calculator in the letter A on your calculator, the letter B on your calculator, the letter C on your calculator, and so forth. If you don't know how to do that, I can show you in class, of course. But that's going to give you the ability to get more exact answers later on. We don't want to use all these rounded measurements to try to find the actual measurements that we're going for later. All right, and now that I found those values of A and B, I know this value of Y that I was looking for is equal to A plus B, and then we're going to say that's 138 plus 181, the stored values that you have on your calculator anyway. And to three significant figures, that's going to turn into 195 kilometers. All right, now the next thing we're going to work on is finding the value of Z right here, for which we said we need to know the values of C and D. So let's go back to this yellow right triangle to find the value of C. We're going to use a cosine in order to do that. We will say that the cosine of 80 degrees equals C over 140, which should give you about 24.3 for C. And then the value of D over here, we'll use a sine function for that because we know the opposite angle from it. The sine of 25 degrees equals D over 200. Then D is approximately 84.5. Now pictures, you can't always trust the way they look, of course. And you're going to see what I mean by that here in a moment. We know that Z is equal to D minus C, and if you subtract those two values, what you're going to get is 60.2. And it completely doesn't look like this can be 60.2, that's 24.3, but we're going with the math. We're not going with what our randomly generated picture looks like because we didn't draw it perfectly, right? Okay, so how did those two values, the Z and the Y, here and here, help us out? Well, one of the things we can do with those is find the value of X. You can use Pythagorean theorem. X squared would equal 60.2 squared plus 195 squared. And so that's going to give us the X is approximately 204 kilometers. And now for the bearing. Well, we said we're looking for the angle between this line that's at the 270 degree mark and this line right there. And we can find that angle that I labeled as theta by using a tangent ratio. We can say the tangent of theta equals z over y. And so then theta is the tangent inverse of z over y. And that is approximately 17.2 degrees. All right. Now, really this alpha is the bearing, because that's going to tell us the direction we're going to fly in relation to 0 degrees or in relation to north. And alpha is going to be equal to 270 minus theta, which is about 253 degrees to 3 significant figures. All right, so let me summarize then. The copter must fly 204 kilometers on a bearing of 253 degrees in order to return from city C to city A. All right, you can see how that gets a little complicated, but you're also noticing how we're just using right triangles to be able to solve kind of some real world problems, honestly. All right, guys, study, focus hard with this. See you in class. We'll work some more. Thanks. Bye.